Welcome to the Valve Studio for April 13th, 2016. Today we're going to get into this thing I got behind me. This is an old vintage turntable that I bought at a garage sale for about $20. And we're going to turn it into a practice amplifier. But first, before we do that, we're going to actually look at the schematic that I found actually inside this thing, kind of embedded in there. And we'll talk a little bit about history. We'll bring up the data sheets. We'll give an estimate of the bias point for this before we actually get in and measure anything, using the data from the data sheets and some other things that I learned along the way. Then we'll actually measure the bias point for that. That's kind of what we'll get done today. And then in the next segment, we're going to look at the power output, the distortion figures, as well as the bandwidth. So let's get to it. All right. All right. First thing is this is it's called a Mectron turntable. I'll go ahead and show you some pictures of it before I took it apart. Like I said, I think I bought this for $20, knowing that actually I didn't want it to get trashed, so I picked it up. I don't really ever pick up turntables. But this guy was he was a good deal. So I never intended to renovate it as a turntable. When I turned it on, the motor didn't spin up, and I really wasn't too concerned about that. But I did take it apart and look at the tube complement, and this was made in the 50s. And so I'll go ahead and talk about how I know that, and we'll talk about its construction, and some decision points that the engineer that did the design of this worked out, and we're able to use the data sheets, and I can go ahead and show you that this design is almost directly lifted from the data sheets for the output tube as well as for the preamplifier tube. So let's get into that right now. This record player is in good condition for being about 60 years old. The hinges work, the clasp works, the handle's in good condition. It's got a 5 1/4 inch speaker, and the grill cloth is in good condition as well. It's got 2 knobs, a volume knob and a tone control. This record player doesn't work because the pinch roller's all dried out and cracked. That's okay, because I'm going to pull out this record player and put an 8-inch speaker in right there. Inside is a tube layout as well as a schematic. It's a Mectron MPA-II. There's not much information on the net about this. That's okay, we have the schematic and we can take it from there. It's a 3-tube design that's directly coupled to the line voltage without a transformer. It's a half-wave rectifier. Single-ended, being powered by a 50L6. That's going to put out about 2 watts of power at 120 volts for the plate voltage. And for the preamp, it has a 12 SQ7. The filaments are in series with a 160 ohm resistor right across the line voltage. Here's the inside of the box. You can see these capacitors are either wax or paper, and those are all going to have to be replaced. And the potentiometers are mounted right to the front plate for that on that piece of wood. There were some mice living in this record player at some point, and they chomped on all the capacitors. And there are also a lot of mouse droppings inside the record player, so I got all that cleaned out. I started reworking this about a year ago, then I kind of had to put it on hold. I picked it up again 2 days ago, and my first thing I worked on was replacing the line cord, and it didn't work. I wasn't getting any filament voltages. You can kind of see down here, all the filaments are in series with a 160 ohm resistor running right across the line. This is really common practice when they remove the power transformer from these record players or radios. was they powered things directly right on the line voltage. But I couldn't find that 160 ohm resistor. I eventually deduced that this little section of green wire right here was that 160 ohm resistor. It's in the right location in the circuit, and it's crimped to the power cord. But that wasn't it at all. It's actually a thing called a line cord resistor. I dug this out of the trash, and it's a piece of 30 gauge wire wrapped between the record player and all the way back to the cord, so that 160 ohm resistor is in the line cord. Here's the first resistor I put in, that 160 ohm resistor. I went and got my, it's getting a little warm, I went and got my temperature probe, and by the time I came back, this thing was smoking, and it cracked, and that failed. So I replaced that with two 80 ohm resistors at about 5 watts. This is functional. They get a little warm, but it's okay. Right now I just kind of got them hand wired into the circuit just to check things. The manufacturer cut corners everywhere on this record player. Here's an example of that. The speaker is physically connected to the transformer winding wire, and it's soldered down to the case. There's not any binding posts, and in fact I had to had to connect this wire down below with a zip tie to the case so that I wouldn't break it off the transformer. I originally thought that they cut these corners to make a lot of money, but when I read that book called How to Get the Most Out of Your Vacuum Tubes, I read something that was interesting. Here's another example of this cutting costs. They didn't hold the hinges on with screws, they used these clasps. It turns out that after World War II, the inflation rate was very high. It's up to about 14%. And you had all these soldiers come back from the war, and they started buying radios and record players. And because the inflation rate was so high, manufacturers had to cut costs everywhere so that they could move products before they lost all their value. So it was a combination of wanting to make money and the inflation rate that drove this optimization to drive cost out of everything. It's very interesting. Well, I couldn't wait to see how it worked. So I plugged in my guitar and I started playing. I got that 5 1/4 inch speaker sitting right on the bench, and volume control here about midway through the scale. And it sounds pretty good. Well, for a 5 1/4 inch speaker. I did eventually connect this up to my big 8 inch speaker, my 4 ohm guy there on the right hand side. And it plays pretty loud for, well, I don't know, 1.5, 2 watts. It's good enough for a practice amp. So we're going to go ahead and continue with this work. Here I am, I'm going to turn it up a little bit. It's not very loud, but it's pretty distorted. That's okay. That's exactly why people have practice amps at 3 watts. The more I learned about this Mectron, the less I was impressed, because there's corners cut everywhere on this thing. But, you know, I got it working, as you could see in that video where I was playing. And I was playing it on this little speaker here, and it kind of got me more energized about what this is. And then I got really familiar with the schematic and the design and, you know, how things were set up in it. And I remember that day I was watching YouTube, and I watched this guy in Japan actually make his own triodes, and he was making really big ones in his I guess he has a workshop or something, and he was making these giant triodes, and he was winding the filaments on there, and he made the plates, and he spot welded the plates together, and he got done with that, and he hooked it up, and it worked. So I'm in here, it's about 11 o'clock at night. I'm looking over the schematic, and I'm looking over this. And it finally dawns on me how really cool this whole thing is with these tubes. I had always had transistors in my life, and you take sand and you make silicon, and you create p-n junctions. This has none of that, which that's pretty obvious. There's no transistors in here. But what's totally cool about this, and it just finally dawned on me, is this whole thing over here is nothing but wires and iron and some glass. So you could, it's just all windings and stuff, and there's a little bit about physics in there with the thermionic emissions. But these guys were able to figure out this really cool thing, and now I can play my guitar, which is made of wood and wire and a little bit of iron in the pickups. It's same with the speaker. All we need is a voltage to this thing and electric fields, and we're playing electric guitar. Then that really got me excited about what this is here. So I don't care how crappy this is made. I'm going to make this thing work. And what we're going to do next is we're actually going to go through it. I didn't measure any voltages in here other than the filament voltages. I intentionally didn't measure any voltages because what I wanted to do was actually look at the design and completely understand it to the point where I can kind of get a good estimate of what the voltages are going to be and what the currents are going to be for both these tubes, and the voltage drop across the rectifier and that kind of thing. And we'll go ahead and go through that right now, and then we'll come in here and we'll measure that stuff on this thing, and we'll see if I, as a verification, that I actually do understand a lot more about this design than I did a couple of weeks ago. Let's get started with that. All right. Here's what we're going to do. We're going to do a circuit analysis of our Mectron record player. So I have the schematic here. I also have the the data sheets for the 35Z5, 12SQ7. This one's for a 25L6, but we have a 50L6, so this is still valid, just a different filament voltage. And here's the one from GE on the 35Z5. So let's start with our schematic. First thing we know is here's the line voltage. I measured this in my lab here, and this number is 120.7. This is VAC. Okay. Now that 120, what did I say, 120.7 times the square root of 2 is 170.7. This is peak to peak. All right. First thing we want to determine is what is this voltage on the other side of the rectifier. So I come over here to my data sheet for this rectifier, and they actually have a chart. If we go through here, look at all these different tables, they have a chart right here for both 120 volt systems and 240 volt systems up here. So you can't read this, but it says the input capacitor is 40 microfarads, 16 microfarads, and this bottom one is 8. So on the schematic over here, our input, the main filter capacitor is 40 microfarads, so that's the top line here. But where are we on the DC current in milliamps? Well, we don't know what that is. What is the total quiescent draw, the Q point draw of the circuit? Well, let's try to figure that out. The major draw is going to be from the 50L6. So we're going to go over to that guy. I can get my stuff straightened out here. This one says typical operating conditions. We're going to go ahead and we're going to pick the typical ones. So if you come down here, it says 0 signal plate current, 49 milliamps. All right. So on our schematic here, we got this current right here at 49 milliamps. With that current there, we can kind of get an estimate of what this voltage is going to be. Because we're on this graph, we're right here, and we come over to here, and where are we? We are on this line right here, and that is 5, 10, 15, 20, 25, 30, 35, 40. That is 140. So if we just take this operation characteristic, we get this voltage out here to be about 140 volts. All right, that's DC now. Okay. So we're done with the rectifier for now. Go ahead and get this out of the way. All right. So that means that there's 40. Oops, this current's not going that way. This current's going the other way. This current's going this way. Okay, so plate current is 49 milliamps going this way. I did go and I measured the DC resistance of my transformer, and this is 225 ohms. 225 ohms. So at 49 milliamps, we get 11 volt drop. It's 100, so at 140 minus 11, we should get over here let me fix this so it's just one decimal point. 129.0 volts. That's our plate voltage. What's the voltage here on the other side of this filter capacitor? I mean this RC network for the screen voltage as well as the anode voltage for our preamp. What is this current? Then what is this one? We can determine what this one is a couple of ways. One way is to come over here and look at it tells us in the typical operating characteristics what right underneath the 0 signal plate current, there's going to be a 0 signal grid 2 current at 4 milliamps. Now there's two columns here. This one is for if the plate voltage is in about 110. This one's for if it's 200. So we're a little bit higher right here because we are at 129. But we'll go ahead and we'll pick 4 milliamps. So that means 4 milliamps is going this way. So there's 4 milliamps going through here. This is a 3500 times 4 milliamps is 14 volts. So 140 minus 14 makes this voltage right here 126. Okay, now what about this current over here? This current, if All right, now here's an interesting thing. When I first looked at this circuit about a year ago, I was beginning to learn about tube amplifier design, and I knew there was two types of biasing. Cathode biasing, which is where you put a resistor on the cathode to ground, and you basically bring the voltage of the cathode up, which creates your negative voltage on the grid. And then there's fixed biasing, where you actually bias this point negative with respect to the cathode itself. So I knew all that. And then I looked at this guy right here, and I was like, what is going on here? It doesn't have a cathode resistor, and this side over here is connected to ground. So how does this, the grid voltage here, get to be negative with respect to the cathode? Well, I eventually found the answer to this is called grid leak biasing. And the way that this works is the filament's down here. It's heating up the cathode. Cathode's kicking off electrons, and some of them are actually hitting the grid, which is making this grid have a negative potential. And then this resistor here is references this to ground. So across this resistor, these electrons hitting this grid induces a current into here, at which makes this grid voltage a little bit negative. And that little bit negative on this 5 meg resistor ends up being around -1 to about -2 volts. Somewhere between -1 and -2. Now, I read somewhere that I was wondering why they chose the 12SQ7. Let's look at that for a minute. 12SQ7 it's used in a lot of radios because it not only is a triode, but it has 2 diodes built into it. So it's used in AM radios for the detection circuit, because it takes advantage of these 2 diodes as well as the triode itself. Well, why are they using it in a record player? They decide to not use the diodes. Well, then why even use this part? Why don't you just pick some other part? I figured it might have to deal with the cost savings that I just talked about. Maybe they had a lot of these. Maybe they were making a radio. They were a radio manufacturer, and they had a lot of these, and they decided to just use these 12SQ7s. That might be true, but the real reason is this grid leak biasing really only works for high mu devices. This 12SQ7, if we go and look at the mu on this guy, we're up at 100 right here. This is pretty high. Now, why is it only for high mu devices? This is the part I spent about an hour trying to figure out what is it about a high mu device that makes it more applicable to be a grid leak bias tube. And it turns out, in order to make a high mu device, the grid is actually closer to the cathode. So the cathode's a lot closer on high mu devices, which makes it so that the electrons that are boiling off here actually hit the grid more often. So they make a high mu device because they need to have this distance very short. Because the distance short, you end up having more collisions, which makes this actually work. All right, so this is about, let's say it's about 1.5. Well, actually, let's look. I think it says in here somewhere about that. Okay, right here. Typical operating characteristics for amplifier in a triode, in the triode unit. It says here the grid voltage is -1. All right, so let's just go ahead and pick -1. All right, just for convenience, that's -1. Now, if we come over here, and we got 126 over here, we have a 500K resistor here, and our grid voltage is -1. So let's look at the characteristic here and figure out where we actually are on this thing. So 126 is about here. And 126 over 500,000 is 0.25 milliamps. Is that right? Yeah. 126 over 500,000. Yeah, 0.25 milliamps. Which is, this is 0.5 milliamps, so it's right in the middle here. So our load line for this triode is way down in here. And up here with a grid voltage of -1, that puts us right here. Which will set the plate current at, ends up being kind of about there. So that is probably about we'll just say 1.25. 0.125. So this is 0.125 milliamps. 0.125 times 500,000 is 63. This voltage is 126. So that makes this voltage over here 64. Get this thing set up right. Okay. All right, here we go. We're getting there. Let's see, what other voltages do we need to find? Oh, we got that one. We got the current. Oh, this one here, the 150. So our current down here is 49. So 49 times 150, 49 milliamps. Come on. Times 150 is 7.3. 7.35. All right, now let's look at the load line for this guy. This is where we get to guess a little bit. Let me get this up here. All right, so this is our 50L6, and what am I looking for here? Oh, here we go. All right. We're not quite matched up directly with this because we have not figured out this volt. Yeah, we did 126. So this is 126 here. Our screen voltage is not quite right. So this graph's going to actually be a little bit bigger for us because they're doing their screen voltage at 110. All right, let's take a look at this over here. So we're at 129 volts up here. That means that we're going to be, let's see, it's 20 per this. That's 20, 40, 60, 80, 20. 129 is going to be about here. So we're going to be somewhere along this vertical line. That's the 129 volt line. And our current, our plate current, is 49 milliamps, so it sticks us right about here. which really kind of puts us almost directly on the -8 line, which is good because we kind of estimated it around 7.5. All right, so we're kind of around in here somewhere. Now what we don't know, we know the load line comes through here somehow. But we don't know what the slope of it is because I did not measure the turns ratio on this. I know that this is a 4-ohm speaker. I do know that. I don't know what the turns ratio is on this. The turns ratio here is going to help us figure out the reflected impedance, and so it's going to actually do something like this here. All right, but that's okay for biasing. We're going to be okay. We don't need to know that slope because that slope doesn't give us any information for the biasing. All right, but tomorrow or the next time we get together, we will take this point and we will need to try to determine that the slope of that, because what's going to happen is that's going to get us over here, and that's going to have us be able to figure out what the maximum power output actually is. All right, what's left on our thing here? So we got this voltage, this voltage, this voltage, this current, this voltage, the screen current, the plate voltage. I got these arrows all wrong. We got that current, we got that voltage, and we know what this voltage is. So I think we're good. All right, we went through and figured all that out. So what I'm going to do is get a different color pen, and I'm going to write down what I measured these things at. Now, you got to trust me here. I measured things after I figured this out. Actually, I'm going from my cheat sheet over here. Okay, so this is how I did it originally, and I came up with these things here, and I wrote one of them in black and one of them in pencil. So what we're doing over here is the theoretical ones are in green, and the actual ones are going to be in black. All right, so what I did measure, this is still valid, 120, because this was measured before. All right. This voltage over here, I measured this DC voltage at the main filter capacitor at 138. So what does that tell you? That tells you that we are actually drawing a little bit more current than what we had calculated for, which means if we look at this graph over here, this graph is telling you is the more current you draw, the lower the voltage on the capacitor is, which means that when we chose 49, which puts us right here, we're actually, when we measured it, we're a little bit lower than that. We're at 138, so we're down, we're over in here, so we're drawing a little bit more current. We're close. I mean, 2 volts is not very much to be off. So let's move on. All right, next one I measured this voltage right here as 122.5, which means we're pulling a little bit more current than what we planned for. But some of that current might be coming out of here as well. We're still okay. All right, we're still at the ballpark. Over here, this is 129. This is for our plate voltage. I measured 127.4. We're looking pretty good. We're off by 1.5 volts. This voltage here, we determined it to be 7.35. I measured it at 8.7. Okay, now that's kind of actually significant there. That means that we picked the wrong current here. And I'll tell you what I ended up doing. I determined this 7.35 by doing 150 ohms times this 49 milliamps. But it's not actually 49. I didn't account for the screen current. So 150 ohms times 4 plus 49 milliamps. So this number is actually incorrect. Let's do that again. 49 all right, so that's 53. 53 times 150, 7.95. Oops, should do it in green. 7.95. Still off a little bit. We're off a little bit, and what that will tell you is that this might not quite be right, because we're a little off over here. So if we were to figure out how we got off a little bit, I bet we could actually fix this up. Because this 126 is theoretical, but we're actually a little bit lower, which means that there's more current going through here than we're accounting for, which means that this 4 milliamps might be a little bit more, which would make the voltage at this point a little bit higher. So we're a little off right in here. So that means that on the data sheet, this zero signal grid current of being 4, this is typically a ratio. So we have 49 here, which is the plate current, over the 4 is some ratio. For our tube, this ratio might not be 49 over 4. It might be something a little bit different. I mean, we're still good. We're still right. We're looking still pretty good. All right, let's continue on. All right, this one I measured at 47.1. All right, now we're way off on this. What's the reason for that? The reason for that is that this calculation here was wrong, which means that on our load line, we're not actually where we expect to be. Let's figure out what the current would need to be in order for this to be, well, we can look at this over here. So if we got 47, we kind of estimated that we're going to be right around here, but in order for us to be 47, that would put us down here somewhere. Is that right? Yeah, it would stick us down at, this is 60, so we'd be down like right about here. Which means that then we're on this curve here, which is the minus 0.5. So then I went in and I said, okay, well, we need to measure this. Well, then what is our grid voltage? So let's measure that. So I put my meter on here and I measured this at minus 0.85 volts. Now here's the problem. You can't just measure this. This is a 5 meg ohm resistor. My little Craftsman voltmeter, my cheapie, is a 10 meg ohm impedance, input impedance. So I'm basically putting 10 megs across a 5 meg, and I'm measuring the voltage. So what happens here is my reading is actually incorrect. I mean, it's close, but it's incorrect. This is actually dragging it down a little bit. So you can't really do that, but that's okay. We're still way off. So I was a little bit disturbed about that. I did a little calculation here, and I went in and I said, well, let's go check this resistor here. On a whim, I checked it. Let me go ahead and show you that resistor over here, if I can get this over here. That resistor is, let me zoom in on this if I can get in there. All right, so there's our circuit here. So this resistor is, oh, this is, I don't know if this is going to work. Where are we? Yeah, here we go. Okay, so these two resistors are 500K, or half a meg. And that is actually this resistor and this resistor. You can kind of see that they're green, brown, yellow. So they're the same value. But I went in and actually measured these. This one's a 500K. This one over here, 770K. That's the problem right there. So I'll go back here and we will back calculate things based on what we measured. All right. I got 0.125 milliohms and 770K. Oops. Did that wrong. 1.5. 770K is 96. This is 126 over here. 29. Okay, so we got several problems going on, but I do know that this resistor here is not correct. Somehow it's degraded in the circuit. So we need to replace this one. Because the reason being, we want this voltage at this plate to kind of be in the center of our load line, so that when we get excursion here, we don't actually get it. We don't go into cutoff or saturation, because we don't want to run off this side, or we don't want to run off this side. So we need to be in the center, because right now we're sitting over here. That might have been the reason why it distorts so easily before it got loud. So that resistor needs to be replaced. All right, we started out with a blank schematic and our 3 data sheets, one for the rectifier, one for the power tube, and one for the preamp tube, which is the 12 SQ7. And the first thing we looked at was we knew our input voltage here, and we wanted to find out what the DC voltage of the main bypass, the main filter capacitor was. And in order to determine that, we needed to know the current through this rectifier. So we went over to the typical operating conditions for the 50L6. We found out that 49 milliamps is typical for these in Class A. So with this 49 milliamps, we looked at the curve for the 35Z5 and found that this voltage was going to end up being about 140 volts. From there, the 49 milliamps is the anode current, or the plate current, and from that and the data sheet from the 50L6, we kind of guessed at the operating conditions for the screen current, which set this at 4 milliamps. With this 4 milliamps going through this 3.5K resistor, that set our voltage to over here at 126 volts. Then we came over here and we were looking at the preamp biasing. We talked a little bit about grid leak biasing. We also talked about how the putting your voltmeter on this grid circuit here. This is a really high impedance node. It's 5 meg ohms. And by putting in your even your digital meter right here, it's a 10 meg ohm input impedance. So it brings this this effective resistance down to, you know, maybe 4 or something like that. The 12 SQ7 was chosen specifically because it's a high mu device, which means that the grid is actually closer to the anode. Because of that, the free electrons that are getting thrown off of here actually collide with the grid, which introduces a current in here, and that's what creates the negative biasing on the grid itself without having it be fixed bias or cathode bias. So high mu is good for this grid leak. Once we knew that, we kind of estimated from the Oh, not that one. We kind of estimated from here the typical operating conditions. Grid voltage is -1. At this voltage over here, where the plate voltage is 100, we're -1. So we said, okay, well, if we're at -1, then what's that current setting? So we put on a come on now. We actually drew the load line over here out to 125. 125 volts is right here. Actually, it's right here. And if you divide that by 500K, you end up being over here at 0.25 milliamps. So here's our load line. And -1 grid voltage puts us right in the middle of this load line. And from there, then we were able to determine what the actual grid current is. And we figured that at 0.125 milliamps, which set the voltage drop across here such that we could determine the plate voltage at 64 volts. We went through and measured all these, and we were very close on all of them. And where we had some discrepancy, I kind of explained that. We talked about this one right here, this 47 volts. This one is actually this one's really much higher error than the rest of them. So that meant that we have several potential reasons for this. One of them is the grid voltage that we kind of guesstimated at was incorrect. That's when we put this meter on here and affected this over here. But we still got a grid voltage of 0.85, which really should have kept us fairly close to where we were, because we estimated we were at 0.1 or -1, but we were at -0.85. So then I came in and I said, well, okay, let's go measure these. Let's measure that and make sure it's 500K resistor, even though it's marked as 500K. It's not. It was 770K. That resistor has failed in the device. 770K is actually going to shift this load line down here. You know, it's going to put it way down here. And that's probably one of the reasons why this amplifier distorts so easily, is the fact that the preamp tube is actually not biased very well. So before I put this back together, I'll go ahead and put this back at 500K. And the rest of the circuit is actually fairly functional. So, got to be honest with you, this is the first time I've actually ever done this for an amplifier. Gone through and figured out all the things, all the voltages and currents, using the data sheets and using things that I've read and all the different things I've read. So this was an exciting thing for me to do today. It was very exciting to actually go measure these voltages and get them to be really close to what they should be. And I found the problem in the circuit as a 500K resistor. I hope you learned something right here. I know I did. Well, that about sums it up for today. We started the process of examining that record player, that Mectron record player. We looked at the circuit schematic. Then we went through and we recapped it basically. Got it to a point where it was playable. Then I wanted to do circuit analysis, which I just did. And we took some measurements, and we found that our circuit analysis really was very close to our measurements. And that was a good thing, except for that 1 voltage on the anode of the preamp. But then we went in to determine that I don't know how old that resistor was, 50, 60, 70 years old, had gone from 500K to 770K, and that was changing the bias on the preamp tube, which was making it prematurely distort. So we have the biasing straightened out. I'll go ahead and fix that. When I come back, we will fire this up. I have a dummy load here. I got two 2-ohm resistors here. We'll put that on there. We will measure the power output. We'll try to measure the distortion, and we'll definitely measure the frequency response of this amplifier and see if there's actually some other things we can do to it to improve the quality. I have ordered a speaker for this. I got a Celestion, and it will come in. I'll go ahead and mount that, and we will have a final checkout at some point. But that's it for today. Thanks for watching. This is the Valve Studio for April 13th, 2016.